webinar. Yeah, thank you for organizing this webinar, and thank you for all the attendees for your interest to this webinar. I hope that you like it and you enjoy it, and I hope I will see you soon in the training sessions. Okay, so today I'm going to talk about application of petroleum geochemistry in both exploration and reservoir management, production, everything related to hydrocarbon production development strategies. The course will be divided in two main sections. I'll talk first about applying petroleum geochemistry in oil and gas exploration. So we'll talk about the applications on the source rocks, maturity, source rock evaluation, kinetics of the source rocks, and fluids, starting with the oil, condensate, gas, organic matter that we extract from source rocks, how we perform or how we check qualities of the oil, quality of the hydrocarbons, how we perform oil and oil source rock correlations to refine our petroleum systems in a basin, in a block, in exploration area. The gas, how we can evaluate gas, starting with the mud gas, for example, that is readily available during drilling, other type of gas that we can get data from them, like headspace gas, fluorine gas, and any PVT gas. There is a small section there which to talk about briefly about how we can use geochemistry inversion to determine the source rocks of like oil seeps, like discovered hydrocarbons in frontier areas without knowing the source rock or without having information on the source rock. And the second section will be on the petroleum of reservoir, what I call reservoir geochemistry. So is petroleum geochemistry applied to reservoirs? So I will be introducing to you how we can use geochemistry to understand the reservoir compartmentalizations or continuity, fluid qualities, all the trapping, post-trapping processes that can occur in a reservoir, etc., and also production allocation. Okay, so let's start briefly introducing what we do in geochemistry. So the petroleum system. What is a petroleum system? If you are an operator, you want to acquire a block, you're in an area, so you need to know whether you have a full petroleum system, which is composed of 5 elements. The most important element, or they are all important, but the starting element is the source rock. So you need to know that in your basin, wherever you are going to explore, there is a source rock. Migration pathways, a carrier bed, a reservoir, a trap, a seal. So all these have to be there, the whole 5 elements, to make up your petroleum system and your chance to progress in your exploration or make any discoveries. So for the petroleum system consists, as I said, with a source rock. The source rock has to be mature. The source rock is not enough by itself. It has to be mature to, in a basin. So you know that it has already done the job, has generated hydrocarbons, whether liquid or gas. So you need a migration pathway, a carrier bed, where the hydrocarbons can migrate when they move out of the source rock. A reservoir, when they can be accumulated, the hydrocarbons. A trap, which is a structural or stratigraphic configuration that focus the hydrocarbons into that accumulation. And the seal, which covers the reservoir or the trap that preserve the hydrocarbons within the accumulation and don't let them actually dismigrate or migrate further or get lost. So the timing of these 5 elements is crucial, and that is obtain using when we do basin modeling. When we do basin modeling, we got a chart that give us timing, for example, of generation of expulsion of hydrocarbons from a source rock. And when you generate, you expel hydrocarbons source rock, you need a trap, a reservoir already there, and the trap already there available to receive the hydrocarbons. Otherwise, there are cases when you've got a source rock, it's materials, generate hydrocarbons, expel hydrocarbons, but the hydrocarbons just get lost because there is no trap, or sometimes they get trapped and then the seal is not that efficient and you lose them. So the timing of formation of all the different petroleum system elements is crucial for in hydrocarbon exploration. Source rock. What is a source rock? A source rock actually is the starting point of petroleum systems. So source rock is there are sediments. Source rock, there are sediments that contain significant amount of organic matter that can generate oil and gas. We have different type of source rocks, oil-prone source rocks and gas-prone source rocks. And the generation of hydrocarbons that we're going to see later on, it depends on the maturity. So depending on the maturity of source rock, we know whether we are expecting to have liquids, oil, condensate, or gas. So, that's examples of different type of source rock. We can see them like outcrops on the left side there. When we drill a well, we can have cores from source rock intervals, and we can have cuttings, ditch cuttings. So let's start with our application of geochemistry in petroleum exploration. Source rock evaluation. Source rock evaluation. The most important thing that for a successful study, successful project in geochemistry is the sampling, and after that, the analysis. So samples have to be really representative, and to answer or to get our objectives of the study, we need really to select appropriate samples, relevant samples for the study, for the objective of the study. So when we drill a well, we can have, if we are lucky, we can penetrate a source rock. So we can have most of the time, it's ditch cuttings, because operators, they don't take cores. They are quite expensive in source rock intervals. So cores are mostly taken in reservoirs. But during the last decade, with the unconventionals, source rock cores also are taken from unconventional source rock intervals. So as I said, most of the time in exploration, in conventional exploration, we got cuttings, and we can get a lot of information, very useful information from cuttings, although we prefer always cores, but we don't have that choice always. But cuttings, I did many projects over my career, and cuttings, you get also very reliable data. In frontier areas, for example, you go outcrops. So the first thing you do, field trip, you go and try to collect outcrops. And outcrops, although they are prone to like weathering, oxidation, but most of the time, as an experienced geochemist or geologist, you know how to do sampling. So you need always to avoid taking the weathered parts of the rock to get reliable samples. We can have from time to time sidewall core samples also. What we do when we do source rock evaluation, we want to identify whether there is a source rock in our well, for example, or in our basin by looking at outcrops. When we collect outcrops or we collect subsurface samples, first thing we know, do we have a source rock there? So to do that, we need to screen our samples for organic richness, which is expressed by the total organic carbon. So you need to analyze samples and determine the amount or the percentage of organic matter in samples, in rock samples. And then we need to know if a source rock if we got a sample which is organically rich, I mean, an interval is organically rich, high TOCs. So we need to understand, the next step is to understand what type of organic matter, what is the quality, what is the potential. That is very important, because then by knowing the organic richness and the type, the quality, potential, then we can predict what we have in our basin. Do we have oil? Do we have gas? Do we have heavy oil? Do we have sour oil? Do we have sweet oil, etc.? And that is very important in exploration activities. So when you screen your samples, so you got TOC values depending on the type of, lithologically speaking, on your rock samples, if it's clastic, shale, claystone. So you can distinguish between poor and very good source rock or excellent source rocks. I mean, excellent organic richness, sorry. Poor organic richness, and there is a difference between carbonate rocks and clastic rocks. So carbonate, you need less TOC relatively compared to almost 50% less than compared to clastic. So if we say like, for example, 1% for clastic source rock, it's fair source rock, but in the carbonate, you can already classify it as a good source rock. I mean, a good source rock richness, sorry. The next step is to, as I said, to determine the type of the type and the quality, the potential of the source rock. So just briefly, the TOC is always, I mean, that is in detail in my course, but we do that screening with a machine called the LECO machine, which gives you the organic richness of your rock samples. So the next step is when you got samples with fair to good, excellent organic richness, then you select them, and then you do the next step, which is looking at the source rock type, potential, quality of the source rock, and that by looking at the source rock potential and the quality, using a machine called rockable pyrolysis. So rockable pyrolysis will give you, as you can see here, a pyrogram, which is composed by 3 main peaks. So there are 4 parameters in total. So you got the S1, peak S1, which is represent the free hydrocarbons, which are already generated from the kerogen from the source rock, but they still in the rock, in the source rock itself. And you have the peak S2, which is actually the source rock potential. So that is the potential of your rock. And the S3 is how the amount of oxygen in your rock, in your source rock or in your. And the 4th parameter is the temperature, maximum temperature at which we pyrolyze or we crack down all the organic matter present in the source rock or in the rock. And that Tmax gives us the maturity, information of the maturity of the source rock that we are analyzing. So on the right side, when you got this information, so what we are looking really most importantly is to the source rock potential, the S2, which is the petroleum potential yield, or the source rock potential. So it could be when you got an immature source rock, it's actually the original source rock potential. When you have an oil mature or gas mature, so that the S2 is always the residual potential, which actually represent what is left in the rock, in the source rock interval, after generating hydrocarbon. So based on this, we can classify whether our rock is a poor source rock, fair, good, and very good source rock based on the source rock potential S2. And then from there, from S2, we can calculate the hydrogen index, which is a very important parameter in characterizing the source rocks, and it's used in classification of source rocks, and also in basin modeling. When you model a source rock, you need to know what's the hydrogen index of your source rock to predict. I mean, the software actually, when you put the information in, gives you the volumetrics based and the type of hydrocarbons that you're going to generate based on your hydrogen index that you put in the model, and also the organic richness. The second parameter is the oxygen index, which is S3, this peak here, times 100 divided by TUC. And these are used, both parameters are used in modeling, are used also in classification of our source rocks. Based on hydrogen index, actually we can say whether our source rock is just, our source or our organic, rock interval is inert, there is nothing in it, especially if it's immature. So if it's immature and hydrogen index is less than 50 milligrams, so there is no source rock whatsoever in that interval. But we can have 50 milligrams with good source rocks, but it's really mature or over mature in gas window. That means initial hydrogen index was maybe 400 and plus, but because the source rock became mature, generated oil and gas, oil, condensate, gas, and now it has exhausted, has finished the job. But so all the values here are applicable for immature source rocks, before the source rocks start to generate. For gas-prone source rock, we have hydrogen equal or less to 200 milligrams. We can have mixed oil and gas-prone source rocks, and we can have oil-prone source rock generate that have 400 and plus hydrogen index. For example, for type 1 source rock, which is lacustrine source rock, we can have up to 1,000. Marine source rock, we can have between 400 to 600 milligram of hydrocarbons per gram of TUC. So that's how we classify our source rocks. Then we come to be able to interpret our data easily, so we can plot our organic richness against the source rock potential, our parameter hydrogen index against oxygen index, hydrogen index against maturity, which is the Tmax. So the organic richness against the potential can classify the rocks, the rocks, whether there is no source rock or post-mature source rock. The potential is low because of the post-maturity. It was initially good source rock, but it has done the job already. So we can have gas-prone source rocks, good oil source rocks, and very good oil source rocks. In using the hydrogen index and oxygen index, we can classify in here on the left side, you got the quality and the potential. On the middle here, we can have the type of your kerogen, of your source rock, of your kerogen. So we can have type 1, which is mostly source rocks deposited in a lacustrine environment. We can have source rocks, type 2. Type 3, which is mostly terrestrial source rocks. And this is type 4, is inertinite, there is nothing there. When we want to know whether our source rock is immature, so there are other maturity parameters that we'll see later on, but as already we're using just a rockable pyrolysis, we can have the Tmax, maximum temperature of each sample, and we can actually combine our hydrogen index with maturity, knowing that with maturity, the hydrogen index decreases in immature source rock. If we start, for example, with marine source rock, which has 600, for example, of hydrogen index of 600 milligram of hydrocarbons per gram of TOC, when the source rock goes through different steps of maturity, enters the oil window, start to generate oil, at that point, the hydrogen start to decrease, because we are converting our kerogen, our soil organic matter, to hydrocarbons. And to produce hydrocarbons, you need carbon and hydrogen. So that hydrogen that is represented by hydrogen index, the amount of hydrogen, the highest amount of hydrogen the most oil prone is the source rock. And the highest is the maturity, the lowest, also the hydrogen index. It decreases drastically with maturity because we are converting our kerogen, our source rock, to hydrocarbons, either liquids or gas. We can use also, in addition to rockable pyrolysis, we can use corrosion microscopy. Microscopy is very important because sometimes we got very mature source rocks, for example, very mature source rocks, and all because oxygen index and hydrogen index decreases with maturity. So all the samples, for example, will be plotting in this region here, less than 20 oxygen index, less than 150. So we cannot distinguish between whether it's type 2 or type 1 or type 3 source rocks. Same here for this plot on the right side. If we have really mature source rocks, for example, if it's post-mature, like in gas or in gas window in this area here, so all the samples will be plotting here, and we cannot distinguish between all these three types of source rocks. So what we can do, what we need to do is that we need to take samples and we prepare kerogen from the samples and look at the microscopy at our organic matter. So visually we can distinguish between different types of source rocks. So these are all immature source rocks because they are quite very fluorescent. When you got high fluorescence, that means the source rocks are immature. So for each type of source rock, you can see that is a lacustrine source rock. So we can see samples representing that, and we've got some mixing also. So B is the representing mostly the marine, and this is how the terrestrial gas-prone source rocks look like under the microscope. They are generally dominated by woody material that they are mostly gas-prone. However, the marine they are mostly dominated by amorphous organic matter, which is very juicy, very oil-prone. You can have algae, you can have polynomorphs, both in lacustrine and marine source rocks. Now, this is the early when, this classification here, what you can see here, is based on Van Krevelen in 1977, where he proposed these diagrams to classify different type of source rocks. So between like type lacustrine, marine, or type 3. But more recently in 95, Pepper and Corvey, they have proposed a new classification, which takes, actually it's more detailed. Because why? Because for example, if I take type 2, I cannot distinguish between type 2 marine carbonate, because type 2 is marine source rock. I cannot distinguish in here between marine carbonate and marine clastic, marine shale. And there is a big difference with them, between them. We can see later on, especially in the kinetics. Type 2 marine carbonate is organic matter. The organic matter is rich in sulfur, so we call it also type 2S. Yeah, marine type 2, the marine clastic, it's actually has got a low amount of sulfur, so generates sweet oils. But type 2S generally generate heavy and sour oils. I give you an example. It's quite widespread worldwide. All the Mesozoic, Jurassic, Cretaceous source rocks in the Middle East are of type 2S. They are marine carbonate source rocks. For example, the most important source rock in North Sea, the Kimmeridge clay, is marine type 2. It's mostly clastic. The Silurian hot shales in North Africa, in the Middle East, it's type 2. It's type 2 marine clastics, shale, etc. So Pepper and Corvey in 95, they combined the type of organic matter and the deposition environment to come up with this type of source rocks. So they classified source rocks into, as you can see here, 1, 2, 3, 4, 5 instead of 3. So first of all, we can distinguish between the marine carbonate and marine clastic. So A is marine carbonate, rich in sulfur. B is marine clastic, poor or low amount of sulfur in the kerogen. So C is the lacustrine source rock, which is the type 1 in our cases. So DE is the type 3 source rock, dirigenous non-marine source rock, but is capable to generate both oil and gas, 50-50. And type F is the equivalent of our, it's a gas-prone source rock, but also can be also the inert. So this source rock here is, we can have two. We can have a source rock which can generate oil and gas, and source rock which is only mostly gas prone. So this is the distinction when it comes to one of the important factor in generation of hydrocarbons, in modeling the source rocks, is the kinetics of source rock. That's why it's very important to know your source rock, your richness, your potential, your hydrogen index, and your type. Is it marine type 2, marine type 2S, lacustrine, terrestrial, etc. So the timing, as you can see in this diagram, so we got the temperature on the left side, and this is the amount of hydrocarbons. So the green of the oil is the oil generated or expelled, the red is the gas. So the type 1, which is, type 2S, which is the A, organophase A, which is the marine carbonate, start to generate and expel much earlier compared to type 2, compared to the others. So we can see here, so timing of generation. So if you do, if it's about like almost 10 degrees between different types, that makes, that geologically speaking is very important to know. And then that will get a timing that affects the timing of generation, of expulsion, and migration, etc., etc. So this is just to go slightly in detail what is happening in each type of source rock, the kinetics. Yeah, when we model a source rock, what we expect. As a geochemist, I know if you tell me I got a type 2S or the organophase A, which is marine carbonate. I know it's marine carbonate source rock. So I can tell you easily what I expect. I expect that in my area, in my block, in my basin, I expect heavy oil and light oil, but the oil is sour. So it's sour, high sulfur content, above 1% of sulfur content. So I have to prepare as an oil operator. I need to prepare myself, my logistics. It's very important. If you have you've got sour type 2 source rock, so you know that likely you will have problems of, you need to choose your proper material, like which are resistant to, for example, corrosion, because sulfur can combine with hydrogen and form H2S or H2S H2SO4, which is a very strong acid that can corrode, the material, tubings, when you sell your oil also, the refinery, so you have, that your oil is sour, so you have this acid, you can form the acid and can attack your, corrode your material. So you have to be prepared for that. And another important thing, we know that H2S also is lethal. So in most carbonate systems, there is H2S, although H2S is formed in the mechanism is you need anhydrate, but in most of this carbonate system, I saw that there is anhydrate and hydrocarbons, and it produce H2S, and H2S is lethal. While drilling operators are always, on alert, just to, if there is any like gas emission, H2S emission, they have to they have to be very, there's high health and safety procedures that is followed. So let's go back now to our different type of source rocks and how they behave and what we expect from them, what type of hydrocarbons we can expect. So for a type 2S, which is a rich organic matter rich or source rock rich in sulfur, so you can see in the kerogen, so that is the chemical composition, roughly. I mean, it's not chemical structure of a kerogen, organic matter. So you can see that there are sulfur combined with carbon. So all these are carbon and hydrogen, and you've got oxygen molecules, so oxygen atoms and sulfur. So when you have sulfur in your kerogen, so you know that how the generation is happening. So you take a rock, you take a source rock. In the lab, what we do, we simulate a generation by using the Rockable pyrolysis. So in 20 minutes, we hit the rock quickly in 20 minutes, and we generate hydrocarbons like S1, S2, etc. The amount of, but in subsurface, this time it is a geological time. So you go a source rock which is subsiding slowly. So with the time and with the increasing temperature and increasing time, you reach a certain maturity. Then when the source rock start to convert, your organic matter start to convert to hydrocarbons. And the reason why type 2S generate early oil, at early maturity, when talking about vitreous reflectance, you're talking about start generating between 0.045 to 0.55 vitreous reflectance. Yeah. And that is because of the presence of the sulfur. So imagine when you hit this kerogen, it's very easy to break down the sulfur or sulfur carbon bonding or bonds, compared because it requires less energy than to crack carbon atoms. Yeah, carbon bonding. So it's so that's, to produce hydrocarbons, you need to crack down these molecules to produce hydrocarbons. So this, because of that reason there, that because of the presence of sulfur, so you actually you need less energy to start to crack your kerogen to convert it to hydrocarbons. So that on the left side, you see the kerogen composition, how it looks in immature source rock. On this diagram here is the activation energy of which is required in kinetics in your source rock. So we can see that's varying between 46 and 52 kilocalories. So it's quite low energy to actually start to crack. Low energy means low temperature, which is the temperature actually at which starts the generation. Because this diagram actually is showing the expulsion. So the generation basically starts earlier, around 80 degrees. Yeah, and then once the rock gets saturated around 100 degrees, you can start to expel hydrocarbons. So what type of hydrocarbons we expect? As a geochemist, I know if I got marine carbonate source rock, that's what type of gas chromatograph I can expect. So that is a high gravity light oil, but it's generate quite high maturity. But the first oil, actually, it's always quite heavy. So the chromatogram will be like containing more alkanes in this site. So these two markers here in red are known as pristine and phytane. They are typically used for determining the type of organic matter and also the deposition environment. So one pristine phytane ratio is less than 1, so it's anoxic environment, and is most likely found in marine carbonate source rocks. And these are the type of fluids that you can get from your type 2S source rock. Early generation, you can have heavy and sour oil. almost like I saw oils that are generated earlier that they go up to 50% of asphaltenes in them, so really heavy oils. With API gravity, you're talking about around 20 to mid 20s. And then the more the source of became mature, the more light or the lighter the oils, the lighter hydrocarbons can be generated and expelled. And also the sweeter. So the more source of become mature, the more you generate lighter oil and less sulfur content until you reach the condensate. You can have also condensate. So, for example, in the Middle East, you go in the commercial side, you have two types of the fluid or the hydrocarbons are divided in two types: heavy Middle East, heavy sour, and light sour. Light, and the price actually is different. The lighter oil are more expensive than the heavy oil because they are contain more hydrocarbons and contain less sulfur than the heavy oils. And then later on, when you pass the oil window, you can actually, the source of can start generate gas also. The type 2, which is like the equivalent for the Cambridge clay source rock or any clastic, the mud B formation, for example, which is the Jurassic in Yemen, the hot shale Silurian in North Africa, Middle East. So all these type are classified as type 2 source rocks. And they are actually quite sweet. They don't have that, they got a tiny amount of sulfur in them. The kerogen most likely the same, look fairly the same as the type 2S. I mean, it's mostly amorphous organic matter. What's the main difference between type 2 and type 2S is the amount of sulfur. The amount of sulfur in the kerogen. So we got here much less sulfur. You can see the difference between the kerogen composition. We don't have sulfur in this. So that means we need more energy to generate hydrocarbons, I mean, oil and gas and condensate from these. So that more energy, that means more heat, more temperature. And the activation energy is higher, so we need more energy. So we generate oil at around 100 degrees Celsius, but we expel it around 110 to 115 degrees Celsius. So it's later than type 2S. And on the right side, the chromatogram is different. I mean, the overall distribution is similar, very dominated by light hydrocarbons compared to heavy hydrocarbons. But for example, if you look at pristine phytane is different. So now we've got pristine dominant over phytane, for example. So that directly tells you that this is clastic shale source rock, it's not marine carbonate. And in terms of the product, so you can generate sweet, light oils, condensate, and gas. So as you can see, the oils are much sweeter. API gravity, when you start to generate, you are talking about around 30 plus, 30 API gravity in starting when you start to generate, and that the more the source of became mature, the lighter became the oil, the higher became the API gravity. Moving now to the lacustrine source rock, which is organic fascist C or type 1. This type of source rocks are deposited in lacustrine, and they've got different organic matter compared to the marine environment. And the kerogen actually is more dominated by paraffinic like components that generate highly paraffinic oils, high waxy oils. The amount, I mean, as the hydrogen index in this type of source is the highest, it goes up to 1000. That means these types of sources, volumetrically speaking, they generate much more oil, liquid hydrocarbons compared to type 2, whether type 2 or type 2S. And they generate also, because they are quite, the kerogen, as you can see on this picture here, it's quite homogeneous, is mostly formed of carbon and hydrogen. So the amount or the energy that you need to crack down this type of kerogen and generate oil, you need higher energy, higher temperature compared to type 2. So we are talking about above 100 degrees Celsius. And you can see it in the energy activation energy is much higher than type 2 and type 2s, okay? So on the right side, one as a geochemist, when I have type 1, I know what I'm expecting. I'm expecting, when I do gas chromatography, I expect waxy gas chromatography. What I mean by waxy is dominated. You can see this one is dominated by light and hydrocarbons compared to heavy, like this one, for example. But here we got having, although this sample actually is a very mature, is a condensate, almost a condensate, but still very contain high amount of these heavy analkanes. Yeah. So and when you look at the oil itself or condensate, this is how it looks. Yeah, they're very, very waxy, and if you take a sample in a vial, you put it in a fridge, you become like wax. And if you put it on between your hand for a few minutes, then it become liquid. So the API gravity here is very high. It's like type 2. It's when it's saturated, it's 30 plus, and it can go. I mean, like these are condensate samples. You can have like 40, 50 API gravity. But the reason why they are waxy is because of the amount of wax in them, of paraffins in them. So paraffinicity or waxiness doesn't affect actually API gravity. It's the pour point, which is quite high. Pour point is the temperature at which the first drop of liquid appears. So for these type of type 1 oils, they got a higher pour point than marine oils. Okay. Now the type 3 that organofascist DE that we say it has got both oil and gas prone is composed of like mixed of woody material and, like you can see here in black, and also some oil prone organic matter like membranes, like cuticles, like resins in this kerogen. The kerogen itself is quite mixed. You can see between type 1 and type 2 in type 3 here, or type DE. So we've got more of these cyclic hydrocarbons or organic matter, which has cyclic, like aromatics and cyclohexane or cyclopentane. So they don't generate. I mean, the oil mostly come from these side chains. So that's why when you look at the kinetics, this type of source rock generate like much less oil than type 1, than type 2 also, and type 2s. So generate less, I mean, like almost 50-50 between gas and oil. So generate oil and expel oil much later, because you need much more energy to actually crack down this type of kerogen. And again, you produce hydrocarbons. This is a gas chromatography, quite waxy hydrocarbons, waxy oil. Pristine phytane is almost always greater than 3. So to differentiate between type 3 and this type and type 1, pristine phytane in type 1 is just above 1, yeah, less than 2 or less than 3. But when you see something like chromatogram like that and pristine phytane more than 3, that's definitely dominated by terrestrial organic matter. And then, as I said, you generate again sweet but waxy oil, and you generate condensate, as you can see here, and you generate gas also from this type of source rocks. The last one, which is the gas-prone organic source rock, that which gives you mostly the gas, yeah, with very small amount of oil, but it's dominated by gas. You see the kerogen is dominated by woody material, mostly gas-prone material. You need much more energy to crack down and produce this gas. and much higher temperature. Gas, you can have wet gas, you can have dry gas, depending on the maturity of your corrosion. I mean, at which stage you are generating, the more mature source of become mature, the drier the gas that you regenerate. And that's what we expect from this type of source rock. So for an operator, you need to know whether you want to go to explore in an area, in a basin, what type of source rocks you have, and that gives you information. You predict, actually, you know already what type of hydrocarbons you are expecting to discover in the basin. Now, the maturity, as I said, so we talk about source rock evaluation, but when you have a source rock, you need that source rock to be mature, either oil window, oil mature, or gas mature. So if it's an oil, if you have in a basin one source rock and it's oil window, it's in the oil window, you know that you don't have gas. You are going to discover only oil. But if you have an oil-prone source rock and it's in the gas window, you know that you are going to discover gas and oil. But if you have an oil source, a source rock that is gas-prone, so you know that you are going to have only gas in your area, but you need that source rock to be really in a gas window. So maturity, what is maturity? I mean, maturity is the heat, with the depth and with the time. So you actually, when you bury your source rock, temperature increases, pressure also increases, and you need the time. I mean, that the geology, it's in a geological time, so you need a really long time to cook your source rock. So a source rock can be immature, and then when you reach the oil window, which are around 80 to 120 degrees Celsius, you generate oil and condensate, and then you pass that stage. You enter the gas window around 150 degrees Celsius to 200, you generate gas, and then if you pass that stage, your source rock is post-mature, so you are in post-gas maturity. It's already cooked, it's already done the job, it already generated oil, condensate, and gas. So if you have an oil-prone source rock in your basin, you expect to have these three types of fluids. I mean, you've got the North Sea, you've got the Kimmeridge clay, which is in some basins, in I think the deep gravens, it's in the gas window. So you have oil, condensate, and gas. So all these hydrocarbons are discovered in the area. So the process is simple. So you got a source rock, you heat it, you produce oil, you heat it more, you produce gas, but sometimes you can have oil accumulations, reservoirs which are at high temperatures, like above 200, 250 degrees Celsius. That oil can crack and also can produce gas. So in maturity evaluation, we can evaluate our maturity of source rocks using pyrolysis, archival pyrolysis, Virginia reflectance, spore colors, biomarkers, etc. So these are some examples of, on the right side, so we've got the spore color, for example, and we look at the spore colors of the sediments to evaluate the maturity, the Virginia reflectance, there are conodonts that they are not commonly used, etc. So this is how we do this. So for Virginia reflectance, we take samples on a whole rock or on a kerogen, we prepare a kerogen, and then we look at Virginia particles and we measure the reflectance. And we got the reflectance values of each sample, and then we can plot them, and then we can obtain a maturity profile for a given well, either for vitrinite or spore in this case. So if you have your source rock, for example, if this interval, your source rock here, you know it's in the gas window, so you know that your source rock has done, if it's an oil prone, has already generated oil and gas. If you have a source rock in this area, you know it's immature, so there is not much going on there. So if you have only one source rock and it's immature, so better maybe take your stuff and leave. So that's very important. So you need to know whether there is source rock and whether it's mature and what maturity it is. With viginate reflectance also there is very important information we can get from maturity profile of viginate reflectance. We can actually estimate missing sections. I mean, we can estimate or calculate the thickness of missing sections in the well. And that can be, it's crucial for modeling, for basin modeling. It's a really crucial information, very key information also in modeling. And we can have also, if we have igneous intrusions, you can have this profile of source. If you have normal faults, for example, we can have this type of profile. So that's so far what just how we apply, I mean, for the rocks. We look at the source rocks, we look at the maturity, the kinetics of the source rock that are applied in modeling to predict what type of hydrocarbons, etc., we are expecting. Now, on the other side, when as a geochemist, also we are interested also in fluids. If we drill a well, we discover an oil or gas, we can characterize this oil and determine the source rock, the source rock type of that oil, the maturity, the deposition environment of the source rock. If the well, if there is a discovery, so we can do the correlation. If the well is dry, we look always if there are oil shows. It's very oil staining, oil shows, hydrocarbon shows. We can characterize all the hydrocarbon shows to determine, to see whether there is, I mean, that a dry well with an oil show already telling us that there is a working petroleum system in our basin, and analyzing the oil shows, so we can determine what type of source rock without actually analyzing the source rock itself, especially if the source rock is not known, is not penetrated, etc. So that's what we do when we characterize oils or oil shows or seeps, oil seeps, for example. So the type of samples we need from fluids, so we need oils, as you can see here. We can analyze oil seeps, as you see on the left side here. We can also, that's oil shows. You drill a well, there are oil shows. It's always very good, important to analyze this type of fluids. From the source rocks, if we hit the source rock, if we penetrate source rock, we take source rock samples after evaluating the source rock and determine the interval. We take samples from the source rock intervals, we crush them, we extract the organic matter, and then we characterize it the same way as we characterize the oils and the oil shows and the seeps. So sometimes we got a gas discovery. So the gas also, it can be collected in isotubes like this, or in isojars, like for the headspace gas. So isojars, headspace gas, you collect cuttings in mud, just take cuttings from the shaker, put them in a jar, an iso jar, which is already has got bactericide to avoid to remove any bacteria, to avoid any producing of biogenic gas within the iso jar. And then that gas that is dissolved, or that is dissolved from the rocks, it is there, and we can analyze it. So it's called headspace gas or airspace gas. We can analyze and we can determine the type of gas, the maturity of gas, whether it's biogenic, thermogenic, etc. So now, if you start with fluids or liquids, oil or condensate, always when we discover oil, we want to know what is the quality of our oil. Is it heavy? Is it sour? So by doing that, so we need to look at the API. We can measure the API gravity, viscosity, put all these parameters, the sulfur content, the wax content, to see whether it's sour, whether it's waxy, whether it's heavy. If it's low API gravity, it's heavy. If it's high, it's light oil. So on this diagram, for example, shows you where the higher is the API gravity, the good quality is the oil, and the more expensive is the oil, and vice versa. In organic matter, we can extract the organic matter, we analyze it by gas chromatography and biomarkers, and we can determine the type of our source rock, also the deposition environment and maturity. more or less the same as doing a rock level, but in this case, it's more detailed, give us more information. And we can compare these detailed analysis of source rocks, of organic matter extraction from source rocks. We can compare it to the oils. So these are the gas chromatography from oils. So when we do gas chromatography in oils or condensate, we can determine the type by looking at the shape. Each shape actually gives us the type of the organic matter or of the source that are generated these oils. We can also look at the quality of the oil. Is it biodegraded? Like this oil is not biodegraded. These are not biodegraded oils, but this is partially biodegraded. So when it's partially biodegraded, the quality is being reduced. It's becoming bad quality oil. And that is just the beginning. That is still okay we can produce it, still API gravity okay. But for oil like this, become very heavy, become like tar. So it's really a very almost immobile oil. So if you discover oil like this, so it's very difficult to produce it. So you need a lot of energy, a lot of money, a lot of high budget to produce that. And it's actually the cost of this oil that oil is cheap because it's not rich in. You cannot produce when you take it to refinery. You cannot produce that much of fuel from that. We use also biomarkers. So we use systematically gas chromatography and biomarkers, and also from biomarkers we can, of oils or source rocks, we can distinguish between different type of source rocks. Or we can say also when there is mixing, also we can have mixing from two different source rocks. So we can unravel that using GC, gas chromatography, and biomarkers and isotopes, etc. So that helps us when you do analyze our oils and our organic matter from the source rocks. We do, as I said, biomarkers, gas chromatography, etc. And then we use the data that we can get, and then we start to build our diagrams, plots, and to try to compare between the source rocks and oils. And that will give us, like, if we're analyzing only oils, we can do oil-oil correlation to see whether we got one type of oil or different populations of oils. Different populations of oils means mainly that possibly there are different source rocks, or there's one source rock that has that the difference is maybe only maturity. So if it's only maturity, so that's one source rock can generate oils at different maturity, but we can have also more than one source rock, and we can actually have different populations. So we can do oil and oil source rock correlations. We can use maturity, biomarkers, aromatics, or other biomarkers. We can assess maturity of oil, and we can compare. We can correlate maturity between different oils. This is a statistical approach, a principal component analysis to carry out the perform oil correlations. We can see here, these oils are from Algeria, and we can see that 4 main type of source of oils, which are most likely, this type here, these 3 groups are mainly different because of maturity, but that one is coming from another type of source rock. From another basin. For the gas evaluation, gas is different from the oil or condensate. Gas, because oil we can do, for oil and condensate we can do, especially oil, we can do many analyses. Like we can look at the gas chromatography, you can look at the biomarkers, isotopes, etc. But for the gas is quite limited. So we know gas, we can have dry gas, which is mostly methane, or wet gas, which can go up to C5. Yeah, sometimes you got C6 plus, but C5, C1 to C5. So the composition, Yeah, but there is not that much that we can do with gas sample, unless, I mean, only we can do only gas chromatography because there is the composition of the gas, and I will show you later isotopes. Okay, so oops, it's stuck. Okay, why I mean, what we can get for information on analyze gas samples. So the type of gas that we can have mud gas sample, we can have headspace gas, flow line gas, and PVT gas. If you just make a discovery, we can collect the gas as DST gas, and we can analyze it. And the analysis of geochemical analysis of gas gives you the nature of the gas, whether it's biogenic, you can say whether it's biogenic or thermogenic. Biogenic is gas which is generated from bacteria. I mean, it's bacteria that can produce gas, which is mostly methane. Thermogenic is a gas that is generated directly from a source rock at different stage of maturity. So we can know what type of thermogenic gas. Is it oil-associated gas, condensate-associated gas, or non-associated gas? We can perform gas-gas correlations. We can, by looking at the headspace or mud gas or mud gas or flow line gas data, we can actually determine the migration style, whether it's vertical in location, in well location, whether it's vertical or lateral up dip. We can determine different type of hydrocarbons zones. So we can like limit the zones. We can say we got here oil zone, we got gas, dry gas, wet gas, we have condensate zone, etc. So we can actually determine or identify mist pay. We can drill well, we can oversee, we can bypass a pay that is contain accumulation, commercial accumulation. So for some reason we can miss it, but looking back at the headspace, I mean the gas data, we can actually find that. We can, I mean, looking at the gas, also we can check the quality of the gas because gas can be also biodegraded. And also we can use gas in reservoir to determine whether the reservoir is compartmentalized or not. So this is a gas chromatography of a gas sample, of gas samples. You can have dry gas, mostly 99% methane. You can have wet gas, which contain all the components. And you can have also, these are hydrocarbon gas. You can have also in addition to hydrocarbons, you can have non-hydrocarbon gas like nitrogen, H2S, CO2, etc. And that we can also determine the composition of the gas. I mean, most of these gas are undesirable, and we don't want to. We want something like that if we are really looking at clean gas, especially for the H2S. We don't want that gas in our samples. So biogenic gas, which is mostly dry gas, so mostly dominated by methane, and is generated by produced through bacterial processes during the diagenesis of source rocks, and it always mostly made at temperature, produced at temperature less than 80 degrees. Thermogenic gas is coming, as I said, directly from cracking of source rocks at higher temperatures. So there is a secondary gas that can be produced, microbial gas can be produced when you biodegrade, when you have an oil accumulation, you biodegrade it. Also, you can produce biogenic gas, which is methane from that. We got different parameters that we can use. We use mostly the composition. For example, when you look at the composition, we look at the gas wetness, gas dryness. We look at the isotopes of the gas, and we can classify different type of gas based on the composition and the carbon isotope and also hydrogen isotope. This just show examples how we can classify different gas. I think if it's bacterial, biogenic will be plotting in this area. Any thermogenic gas will be there. We can have mixing, biogenic and thermogenic. We can have, like in here, oil-associated, condensate-associated, non-associated gas. We can also determine the maturity. You can see in this diagram, the more mature the source rock, the drier is the gas. Also, we can, determine if the gas is plotting in here. We can say that this gas, roughly, we can estimate calculate the maturity at which the gas was generated. Now, for the headspace or mud gas, how these data are used. So it's quite popular, this type of diagrams, which shows the evolution of the balance and the gas wetness and the gas character. So what is the balance? The balance is the amount of methane and ethane divided by propane to C5 pentane. The gas wetness is the total of C2 over to C5 divided by C1 to C5 times 100 if you want to do it 100%. And the gas character is the amount of your heavy components, butanes and pentanes compared to C3. So when we plot these parameters obtained from mud gas, headspace, or flow line gas against depth, so we can, by looking at the profile of these parameters, of these ratios, we can define different zones of hydrocarbons. You imagine if this is a well, so we look at the gas wetness in green. So in green, in this interval here, the gas wetness is very low, so it's very dry. So we have very dry gas. And then with depth, in this interval, we have the two curves, the wetness and the balance are intersecting. And this is where it becomes interesting. So this is where you can have, and when you got something like that, it's where you have light oil or condensate. And then when you got higher wetness and lower dryness, so this is where you have an oil, an oil accumulation. And we can see the character, and the character also is increasing in this. So that means the heavy gas components, they are dominating over the lighter ones. This is because we got oil. So in gas, we don't have this heavy in gas zones. The minute we start to hit like an oil accumulation or condensate accumulation, the gas character increases. So that's this type of data is already available during drilling. So we can have already an idea if we are actually penetrating hydrocarbon accumulation and what type of hydrocarbons. Is it dry gas? Is it wet gas? Is it condensate? Is it light oil? Is it heavy oil? Or is it just residual oil? Residual oil is when you got an oil there and that oil disintegrated and you got only like the very tarry, very bituminous hydrocarbons left in the reservoir or in the carrier bed. You can do this, also apply this type of data. This is a lateral well, yeah. So we got a gas and oil. So you can, you look at the composition of methane, ethane, up to pentane, and these are the parameters: balance and gas wetness. For example, in this area here, we got gas, dry gas, and then we enter the oil accumulation. We're there. And then when we go to the oil, to the water, so that is just a residual oil. So there is a residual oil here. So we can actually using the mud gas data, we can follow the drilling. So we can actually guide what they call it steering drilling. So we can guide the drillers, whether they are in which zone they are. Are they in the gas zone, or are they in the oil zone, or are they in the water zone? So we can guide them through drilling. And this can be done, I think, on site, on the well site. Okay, so that's briefly about what we do with fluids. There is one thing that we can do in geochemistry that we call geochemistry inversion. I just mentioned it briefly earlier. So when you drill a well, you can have dry gas, for example, dry wells, like these wells, for example, dry wells, but they have oil shows in them. Or you can have a well, you can discover oil, for example, but you don't know. If you drill a well here, your source rock is this red section. You can have also in this side here, but you don't know anything about the source rock. You drill this well, you don't penetrate the source rock, So and you discover oil. So what do you do? So how do you know what type of this oil, where type of source rock was, from which type of source rock was generated? Or if you are wandering in a field trip and you discover an oil seep, you collect it, you don't know what to do with it. How can you know where this oil seep or oil show coming from? So the first important information when you find hydrocarbons, that means you have a petroleum system working. You have a source rock, and source rock is mature and has generated oil. Now, to determine the type of source rock, the maturity, the likely age sometimes if we are lucky. So you can do geochemical analysis on these oils, do biomarkers, do isotopes, you do things, and then you can track back your source rock. You can determine by looking at the gas chromatography as we saw here. You can determine what type of source rocks and maturity of your source rock. And sometimes when we are lucky, we got some biomarker, which are age diagnostic biomarkers. We can find them in our, for example, for tertiary oils, late Cretaceous to tertiary source rocks, they have a marker known as oleanine. So if you have this marker, you know that definitely that your source rock or your oil was generated from at least late tertiary or middle to late tertiary source. Depending on the abundance, you can say whether it's tertiary or Cretaceous source rock. So we can have this. We can have these examples, and I did myself many studies like that, and I managed to track back the source rock, the maturity, and the type, etc. Moving now to the second part of this presentation, it's how we use petroleum geochemistry in reservoirs, in production development strategies, reservoir management. What is called, it's known as the reservoir geochemistry. So geochemistry applied to reservoirs. So what we can do in this when doing reservoir geochemistry in reservoirs. So in this case, we are interested in exploration. We were interested in source rocks and fluids. Now we are interested mostly in fluids. So by analyzing just the fluids, we can track back the history of field charging, whether the reservoir is compartmentalized or not, whether we got good quality, bad quality oils. We can find out the fluid contacts, see whether we have tar mats formation in our source rocks, etc., etc. So, and that can help both production and exploration also at the same time by looking at, by finding the information of by understanding how the reservoir was charged and determining the filling points and directions, we can actually guide the explorationists in their operations. By reservoir compartmentalization also can also guide because that will give us some information on how the reservoir was charged. Looking at the quality of the oil, also we can guide the explorationists that what we can expect, what type of fluids you expect, which are all important parameter, important information in oil and gas industry. Example, for example, the oil quality. When you got an oil, you got a reservoir, you collect an oil, either a DST oil or oil from the wellhead. You look at, you do just gas chromatography, and you can check whether your oil is non-biodegraded, is well preserved, whether it's partially biodegraded, like these two here, or whether it's really heavily biodegraded. So, and by knowing other parameters like the temperature of your reservoir, the type of your oil, the quality of the oil, you can actually predict other reservoirs, what you can find in other reservoirs that they are undrilled. For example, if you are an operator, you want to drill, you made an accumulation, the reservoir is, for example, at 1500 meters, the oil is biodegraded, temperature is like, that is about 60 degrees, for example. So you can use that information to predict what you can find in a deeper reservoir or in a shallower reservoir like this. So you will be targeting, maybe if you have reservoirs for 2 kilometers and deeper, your maybe operation, your priority will be targeting this type of reservoirs because you will be less prone to biodegradation. So you will have oil with good quality. So if any reservoir which has more or less the same characteristic of the reservoir that has biodegraded oil, low temperature, etc., so you expect that you have biodegraded oil. So that's something. So also we can actually predict oil quality in different compartments of a reservoir. So for example, these are 3 platforms here of horizontal wells. These are all horizontal wells. So when you drill a well, you can collect cutting samples in a reservoir or core samples, and then you extract the residual oil, and then you can characterize it. And then you can estimate, you can determine, for example, the quality, the API gravity of your oil in that particular samples. And then you can map this. If you have several wells, like in this example, you can map where your good quality oils are and your bad quality oils are. So now, if you come today and you want to drill a well, you're not going to drill a well in this compartment here or in this compartment. You are going to drill a well in this, in here, in here, in here, in this compartment here, and to less extent in this compartment here. Then you know that you're going to be hitting good quality oil that you optimize your production. So that's this strategy of working. So you are trying to using geochemistry of existing drilled wells, taking rock samples, looking at the residual oil, obtaining the quality of the oil from this type of samples, and then you can plan where your next, for example, development drilling should be. Yeah, so that's the examples of compartmentalization in reservoirs. So in this example, we have a reservoir which it's faulted, it has got different compartments. We wanted to know whether there is connection between 2 and 3 in this particular case. So when we did we take our oil samples from each compartment, and then you analyze them, gas chromatography, biomarkers, and then you do your correlations. This shows that compartment 2 is completely different from compartment 3. That means there is no connection whatsoever. So reservoir is compartmentalized, and so on. So you can have wells from different compartments. You've got like these compartments are separated by faulting. In this case, sealed faulting. So it could be, sometimes you can have permeable faulting, and we have also 2 reservoir horizons. So when you do geochemical analysis, you see that the composition of this oil is different from, that means there is no connections between these 2 reservoirs, and also laterally, also there is no connection between this and this and that and that. So that all done by geochemistry, and it's very cheap. You take oil samples on the wellhead, or DST samples if they are taken during when they do this discovery. But if you take cheaper samples, you just take oil samples from the wellhead or from the separator next to the wellhead, and you can do very cheap analysis, and you can really find out about your reservoir distribution or fluids in reservoir in a very cheap, with a very cheap expenses compared to what the engineers do. Without closing, without shutting the production. So the production is ongoing. You take a sample, but some of the, correct me if I'm wrong, some of the engineering operations, they have to close. For example, they have to shut. For example, I don't know if the reservoir, the deepest, for example, they try the shallowest, and then vice versa. If they want to check, for example, if there's the same pressure, they maybe shut well A and keep these ones, and vice versa, etc. So that costs money. But geochemistry, production is ongoing. You take just samples from wellhead, and you get the job done. So this is laterally. Vertically, you can have the same thing. You got a barrier here, you got samples from the top reservoir, samples from that. You can do some geochem, like in this case, API gravity, in this case, biodegradation. So you see the differences between two compartments, that there is a barrier, there is no connection between the reservoirs. In terms of fluid contacts, so you can take reservoir cutting samples or core samples. You just extract the residual oil. You quantify the residual, or how much per sample, and you measure or you calculate the different percentage of your residual oil in hydrocarbons and non-hydrocarbons like asphaltenes. In gray here is the hydrocarbons, aromatic, and the thing with the dash here is the aromatics. These are hydrocarbons, and the black is the asphaltenes and polars. Reason said asphaltenes. So from here, this is done by a technique called chromatography, which is a different type of chromatography. It's called iatroscan, or thin layer gas chromatography on residual oil extracted from reservoir rock samples. So when you analyze them, you see, so you measure the abundance of your total residual oil yield. So that the highest is, so that where your oil zone is. And if you have very low amount of your residual oil and dominated by asphaltic and polar compounds, so that's where you have your oil or your water zone. So you can limit your oil-water contact easily using this technique. And you can have also you can differentiate also residual oil from just water. The same in this well, so you can see that. Initially, this well, I remember it was from my thesis. They based on the log, because engineers they do this oil, they determine the oil, the hydrocarbon zones or the fluid zones by logs. So by logs, but sometimes it can be difficult, especially if you cannot do reliable data. So you can take samples and you can do that. So originally the log water contact was delimited here, but then when I did analysis on this core sample, these are core samples, I found out that there is a zone here that was bypassed, which can be like another secondary oil zone. So that's the primary one, that's secondary. So we can easily produce also oil from them. So, but if initially we just take care of this one and we ignore that, so we are losing, so to enhance, to optimize production, so we need to go down and perforate in this interval. And the water zone actually is mainly here where there is nothing there. Okay. So one of the problems when you got a reservoir is that when you estimate your volumetrics, your volumes of your reserves of, so sometimes if you don't know whether some of the reservoirs, they have a layer of tarmat. Tarmat is a solid, can be solid bitumen, which has got high amount of immobile oil, asphalt, dominated by asphaltenes. So if you have a layer, and the layer can be going up to a few meters, and you don't detect it, you don't identify it, you think that the whole column is oil, is mobile oil. So then your reserves are not well constrained. So by doing the geochemical analysis, you can actually identify the tarmats in a reservoir and can understand also, we can understand why we have tarmat, the process or the mechanism of the formation of the tarmat. They are undesirable in a reservoir because they are immobile. Tarmat can be, can reduce the reserves, I mean the oil in place, the oil that it's produced, that can be produced, and also can also play the role of a barrier, can become a barrier. They can actually disconnect the reservoir in two compartments vertically. So it's really important to know that. then when you drill a well, development well, you know where you have to perforate to produce, to optimize your production. You don't need to optimize you can drill a well and you just perforate above the tarmac zone or just below. So you are missing either parts, or when you perforate within the tarmac, you're not producing, it's just heavy oil. So it's very heavy, you cannot produce it. The last thing, I think it's production allocation. This technique is when you drill a well, for example, you discover a reservoir with two horizons like this one. Yeah. Then you want to know, so you take a DST sample from here, you decode DST from here, you say you store it and properly, and then through time you start to produce, and you don't know which reservoir you are really producing. Are you producing mainly from here, or mainly from here, or from both? So through the time of production, you can take samples. You can take samples on wellhead, and each time, for example, if you start today, for example, 18th of June, you take a sample, you analyze it, and you compare it to the end members, DST1, DST2. You can take one in another one in the next month, and the other month, etc., etc. And then you can actually follow your performance of both production from both reservoirs, where you are producing. Are you getting mixed, or are you getting more from that, or are you losing the performance from reservoir one, the deeper, or performance from reservoir two, etc. So we can do that through time. And what we do, as I said, we take the end members. If you got an end member from reservoir, shallower reservoir, that is deeper reservoir, in the lab we can mix different proportions, known proportions of our oil M1 and 2. We can mix them different proportions, and when we take a sample from actual sample from the producing well, and then we do our geochemical analysis, and then we compare between them. They can take different parameters, ratios, and we correlate them with the amount of the proportions of the oils, and then we can find out our oil that produced today, what's the proportion. So in this case, for example, we are producing about 72% from oil 2, and only 30%, 28-30% from reservoir 1. So that type of things. So there are different examples that are shown here. And this example, for example, we have this one. The pink one is from this member, reservoir member. The red is from the 40s member. And we actually made a 50-50 mixture of the oil, which is plotting in this. And today's produced oil actually is in green. So we directly see that our commingled produced oil is mostly actually being produced from that reservoir already. And we can actually calculate how much. In this case, I think and you can see through time how the production has evolved. So this is the 40s, which is we started as producing 60%, almost 50%. 50% from the 40s, but then the 40s reservoir became less active through time. So nowadays we are producing more from that reservoir. So that kind of thing that we can find from production allocation. For this, I finished my